Okay, good morning. So we continue the lesson of set theory. So far we actually introduced the notion of a set. Yes. And then we also introduced the notion of subsets. And then the universal set. And then using the notion of the universal set, we also define the complement of a set. Yes. So these are the things we have studied so far. But now we want to learn how to operate amongst sets. For example, when we discuss about numbers, we learn how to operate among numbers by adding them, subtracting them, multiplying them, dividing them. So we want to define some operations on sets. The operations that we look at, these are the only operations more or less in set theory. One of them is called the union of two sets. So let me write just the names. So the union, intersection, and subtraction. And subtraction. So okay, I think that we will probably be able to discuss the first two. The next one will be left for the next lesson. Okay, so let us start with the union. So the union of two sets, I give you two sets, A and B, and then I ask you to union them. The symbol we use for the union is this. It's not U, it's like U, but you put them in between and you read them A union B. A union B is the set so that the elements of that are either in A or in B or in both. That's just unioning them. So if I want to define them rigorously, I would say that the union of A and B consists of all elements, which are all, of course, are coming from the universal set. So this is the symbol that we use for the universal set, such that X belongs to A or X belongs to B. So this symbol means or. Okay. So here we talked about the Venn diagram, yes? Yeah. Okay. So for example, if you want to visualize what is the union, we can draw a picture here. For example, do you remember a Venn diagram? I forgot to put that here. We also learned about Venn diagrams, yes. The Venn diagrams are a tool in our hand to visualize the abstract notion of sets. Okay, so and then the convention was that you draw a rectangle and then you call it the universal set, and then whatever set you have, you put them inside this rectangle and usually draw circles for them. So for example, if this set is A and let us say this set is B, the union of these two sets means those elements which are either in A or in B or of course in both. Okay, so these parts that I am making clear are the points, are the elements which are within A only. Okay, these are acceptable, and these points, these elements are only in B. These are also acceptable, and now these points are also acceptable because they lie in both of them. So in total, what you see here on the picture, this is A union B. Okay? As a simple example, if I give you A to be 1 and 2 and 4, for example, and if I give you B to be, say, 1, 5, 7, and 4, and if I ask you union them, okay, it means that write all elements which are at least in one of them. Okay, so A union B becomes, for example, I start from the elements in A, I write all of them without consideration, and then I start appending the elements of B to this. Of course, if there is already 1 there, I don't write 1 here, because I told you that in sets we do not repeat elements. So 1 is already there, but 5 is not there, so I append it here. 7 is not there, so I put it here, but 4 is already there, so I close it. So this is the union of two sets. Yeah? So these are the elements. So if you see 1 is in both of them, 2 is in A but not in B, 4 is in B and A, 5 is in B not A, 7 is in B not A. Okay? These elements are at least in one of them. So this means that this is the union. And of course, if I ask you what is B union A, I hope that you agree. Of course, might be you start from writing the elements of B first. Yes? But then you start appending the elements of A to what you have written, but 1 is already written, so you don't write it, you write 2, and 4 already written, you don't write it. And then of course, if I ask you, do you think that these two sets are equal? You would say yes, because they consist exactly of the same elements. The only difference is that might be the order is not the same, and the order is not important when it comes to sets. Yes? Any questions here? For example, if I want to draw another scenario, so if I, for example, take this Venn diagram here, and then let us take A to be like this, and B to be like this, okay? So where is A union B now? The elements are in A, or in B, or in both. But of course, there are no elements that are in both, but I have to color everything that I see in A, yes, and everything that I see in B. So these together becomes A union. Okay, any questions? So that is very simple. That's an operation we do with sets. So whenever you see this symbol, it is called the union, and then the left side and the right side should be a set. But of course, it doesn't matter if I want to union more sets. Okay, so for example, if I give you another set, say 2 and 9, and if I ask you what is A union B union C, of course there would be a question, might be because I have two operations, you might ask, okay, is it important to do which one of them first? Hopefully you realize that it doesn't matter. If you do A union B first and then union it with C, you will get the same answer as if you union B and C first and then union A with the result. Okay, so in that case, if I ask you what is the union, what is the answer? So I have 1, 2, and 4 there. Yes. And then I have 1, which is already written for B, 5, I add it here. And then I have 7, I add it, but 4, I do not add it. So B is finished now. I go to C, C is 2 and 9, 2 is already theirs, so I don't put it, and 9 is there. So this is A union B union C. Okay? And it is important to see that there is no difference between doing this first and doing that first. The result between them will be the same. So this is called associativity, yes? Yes, this property is called associativity. Of course, associativity is not something related only to the union. For example, if I give you 3 numbers and I ask you to add, you never ask which one I have to do first. The reason is that this operation is associative, meaning that grouping them does not matter. If you do them in that way or you do them in that way, the answers will be the same. So this is why you really don't ask in which order I have to do it, because it doesn't matter. And the same is true. So if I have the union of three sets, it doesn't matter if you do this one first or you do this one first. This is why we don't need to put pairs of brackets. But this is not always the case. For example, if I give you this in the exam, this is not clear what I mean. Yes, because here I have two operations, both of them are division. You might interpret it as this, or you might interpret it as this. In the case of addition, it doesn't matter how you interpret, the results are the same, but in the case of division, it matters. For example, if I ask you what is the answer to this one, this is just 2/3 divided by 4, so it becomes 1/6. But if I ask you what this is, so this becomes 2 divided by, this time I have to do this one first, so it becomes 3/4. And if I divide that one, it becomes 8/3. And then you see that the answers are not the same. Yes? So it means that we say that addition is associative, but division is not associative. So if it is not associative, and I insist to give you this, I have to make my mind. Either I have to give you this to calculate or that one. There is no way that you understand my intention. By putting pair of brackets here, I am telling you that prioritize this division. If I put the pair of brackets there, I am telling you prioritize that. Okay? But if an operation is associative, I really don't need to be explicit. In any way you do it, you will get the same result. So the notion of associativity is not something related to sets and the union operation. It is a generic idea in mathematics when it comes to operations. So, and this one, that A union B is the same as B union A, is called commutativity. Yes? So A union B is equal to B union A. This is called commutativity. Yes. So it means that the order in which I am doing this operation is not important. For example, do you think addition for numbers is commutative? Yes or no? Addition for numbers. Addition is commutative, yes, because 2 plus 3 and 3 plus 2 are the same, no matter what the numbers is. So when I want to add two numbers, I don't keep the order. I don't need to keep track of the order. So I would say that addition is commutative. Is subtraction commutative? No, because 2 minus 3, for example, and 3 minus 2 are not the same numbers. So we say that this operation is commutative. This operation is not commutative. So if I want to say it in words, I would say that union is associative, union is commutative. So it means that you don't need to worry about the order in which you union the sets. You don't need to be worried about which union you have to do first. Okay, so that is very generic. It is good to know about that. Okay, so for example, if I ask you what so let me also try to understand a little bit more. For example, what do you think if I pick up a set in my head and don't reveal the elements to you, can you write something for this? I have a set, I want to union it with the empty set. So unioning two sets means appending the elements, yes? So I have a set, I want to union it with the empty set. What do you think the result is? The original set, yes? So it becomes the set itself, because you write the elements of A, and then you want to append the elements of the second set to that, but there is no element there to append, so you close. It becomes the set itself. So if I want to read it in words, I would say that the union of every set with the empty set is equal to the set itself. Yes? Okay, so that is simple to understand. Now, what do you think will happen if I take a set and union it with itself? So in numbers, if I take a number and add a to it, it does not become a itself, it becomes 2 times a, yes? But when I have a set, union it with another set, with the same set, it becomes the set itself. So why you do that? Because, for example, if I want to union this set with itself, I open a curly brackets, I write the elements there, and for the first one, and then I want to append the elements of the second one, which in this case is the set itself here, but on the condition that I am not allowed to repeat anything. But because every element is already repeated, so I close it. So this means that the union of every set with itself is the set itself. What do you think will happen if I take the set A and union it with the universal set? Yes? It becomes the universal set. Is that understandable? Yes? Because the universal set contains all the elements of any sets. So when I want to append something to the universal set, I cannot add something new to it, because whatever is in A is already in U. Yes? So when I write the elements of U, I want to append new elements from A, but there are no new elements from A because the elements of A are coming from. So, and then another property might be good to understand. Do you remember what was the notion of the complement? So if I take a set and union it with its own complement, yes, so what happens then? It becomes a universal set, yes? But do you remember what was the complement? Complement was whatever is not in the set itself. It's in the universal set, but not. But these are, so you see, these rules, they are scattered among exercises, but these are very important to realize, so it will help you a lot. Any questions so far? So it was very simple. The union is a very simple idea. Okay, the second operation that we want to talk about is the operation of intersection. Okay, so actually that's also a good name, like union. Might be you can guess what is the meaning of intersection. So intersection means the elements that are in common in both of them. So the common parts, you call it the intersection. Okay, so if I have two sets, A and B, intersection is symbolized by the opposite symbol. Okay, A intersection B. Okay, I don't think there is a matter of confusion because union is very similar to U for union. The opposite one is intersection. Okay, so when I say A intersection B, I mean the set consisting of all elements from the universal set, but not all of them, such that that element is in A and in B simultaneously, yes? So this symbol means and. Exactly, you can say the overlap between A and B is the intersection. So if I want to understand it from a Venn diagram point of view, so what can I do? For example, let me say that this is my universal set, this is my set A, and this is my set B. When I say A intersection B, I am interested in those elements which are simultaneously in both of them. And hopefully you agree with me, this part is representing A intersection B. Yes? For example, if I want to draw this, I want to highlight intersection for this scenario. So where will be intersection? There won't be. So when you say that there won't be an intersection, it means that the intersection is what? The empty set. And then there is a name for that. If two sets are in a way that the intersection is empty, we say that the sets are disjoint. Okay? A and B are said to be disjoint. Disjoint sets. Okay? And if I want to give you a little bit more concrete example, so So what we can write, say that this is the sets that we have here. Let us just use them. Here, this is my set A, this is my set B. Now I want to find the intersection. So intersection between A and B means what? Means find all elements that are simultaneously in A and B. So one is in A and is in B, so it is allowed to be in the intersection. 2 is only in A but not in B, so I don't write it down. 4 is in A and also in B, so I write it down. Is there any other element such that it is in both of them? No, so that is the intersection. Yes, is that clear? Okay, so for example, let us solve an exercise here. Now, before doing that, let us also talk about that. What do you think in your idea? So do you think that intersection operation is associative? What does this sentence mean? This sentence means that if someone gives you 3 sets, it doesn't matter if you intersect A and B first and find the answer and intersect it with C, or you intersect B and C first and then intersect it with A. Do you think that the results will be the same? Yes? Yes, that the results will be the same. Hopefully you are convinced. And so this means that this operation is also associative. But about commutativity, what do you think? If I write A intersection B and another person writes B intersection A, what do you think about these two? They are the same. So remember this. So both operations that I have introduced so far, meaning union and intersection, are both associative and commutative. Okay, these are big names, okay? But in principle, it means that if I have intersection or union, I don't need to be worried about in which order I am doing them. I don't need to be worried in which group I am doing them, okay? The results will be the same. Okay, but we can also write something similar for these. Okay, for example, so let me write, I don't know, 1 prime, yes, and 2 prime, 3 prime, and 4 prime. The counterparts of these. So if here I would say a set union with the empty set is the set itself, but a set intersection with the union with the empty set is what? I want to find the overlap between a set and the empty set. I am interested in all elements that lie in both of them. Yes? The empty set, because there's nothing. Yes? So this will be empty set. But now, similar to this, I take a set, whatever you like, I intersect it with itself. What will happen? I am interested in all those elements that lie here and there. The set itself again. Yes? And then, similar to this, if I want to write something like this, I would write intersection with the universal set. So what happens? I want to intersect my set with the universal set. So say A is my set, and this is the universal set. Don't look at B. So where will be the intersection? The set itself. And then finally, if I take a set and intersect it with its own complement, the answer becomes the empty set. Yes, because A and A complement do not have any overlaps by definition of the complement. So you see, these are very natural things to understand. Okay. Let me talk a little bit about distributivity. That would be a little bit more interesting and a little bit harder. So do you remember distributivity? Distributivity. Have you heard about the name? So when we have it, yes. For example, let us go back to the numbers that we are familiar with. We have 2 operations, multiplication and addition for numbers. Okay? We say that multiplication is distributive over addition. What do I mean by this sentence? It means that if I give you 3 numbers, if you add the result if you find the sum between B and C, and then multiply A there, you can do it in this way. Yes, we know that. So if I tell you multiply A in, you just multiply it, but what you are doing is called distributivity. It means that you take multiplication and then distribute it over addition. You see, you had only one multiplication here, but when you look at the right hand side, you have two multiplications. So you are distributing this multiplication over B and C. So you're distributing multiplication over addition. Yes? And we know that this is true. So that is called distributivity of multiplication over addition. Okay, let me just test your understanding. Do you think this operation, so this operation is distributive over this operation? What about the other way around? Do you think addition is also distributive over multiplication? First, tell me what the meaning of this is. Let us assume for the moment that yes, addition is distributive over multiplication. What does this mean? If this formula, if this rule is correct, how it looks like. For example, if I say, when we say multiplication is distributive over addition, how it looks like, you write this formula for me. Okay? Now let us assume that we don't know if it is true or not, but I wanted to see how it looks like. If addition is distributive over multiplication, how it looks like if I want to write a formula. Yes?
Is it if A plus B times C
Yes?
equals, is it A plus B times C?
Yes. If this is going to be true, it means this. This is what I want you to understand. I'm not telling this is true or false, but I'm telling you, if it is supposed, if this is the case that addition is distributive over multiplication, how it looks like this. It looks like that you are taking addition and then distributing it over multiplication. So let me emphasize that here is this operation. Okay, so if I want to emphasize, you see, this operation repeats itself here and there, and this operation will be here. Now, let us see what happens. Instead of multiplication, I have addition. It is repeating itself here and there, and then this operation is here. So yes, this is how it looks like. Yes, but I'm not telling it is true, and you know it is false. Yes, for example, so this one is true, which we use it all the time, even from Math 1C. If I ask you to multiply that, this is the way that you do it. And this looks unfamiliar to you. The reason is that because it was not true, otherwise teachers have already told you that. So this is false. If I want to understand why this is false, for example, I can choose A to be 1, and B to be 2, C to be 3. And if I calculate the left-hand side for this one, what is the answer? It is 1 plus 2 times 3. But what is the answer to this? Is 1 plus 6, which is 7. But if I calculate the right-hand side, what will happen? It becomes 1 plus 2 times 1 plus 3. So this becomes 3 times 4, which is 12, and you see that they are not equal. Okay? So the reason that you haven't seen this formula before, because it was wrong. Okay? But if it was true, we could have said that addition is distributive over multiplication, which is not true. Okay, so let us take it over. Yes, let me take it off. Okay, but now be careful. There is here, how many numbers are involved? 3 numbers, but we have 2 different operations. Associativity also involves with 3 numbers, but with the same operation. For example, I can say A plus B plus C is equal to A plus B plus C. Yes? I have 3 numbers involved, but the operations are both the same. Or, for example, I can write A times B times C is equal to A times B times C. Again, I have 3 numbers, but I have two operations, but both of them are of the same type. In this case, both of them are multiplication. But distribution is different. In distribution, I have three numbers again, but I have two different operations. And then I can ask, is it the case that one of them is distributive over the other one? Okay? Now, let us go back to sets. We learned two operations, union and intersection. So far, union was enjoying the property of associativity and commutativity, exactly like numbers. And we also had this for the intersection. But now I want to ask the same type of question. Do you think, now, but this is my question. Do you think the union is union? So this means union, yeah? So let me write it in words. Is union distributive over intersection? Okay, what about the other way around? Okay, the second question is intersection distributive over union? Okay, we want to answer these two questions. Okay, before answering these questions, we need to know how they look like to see if this is true or false. Yes? Exactly like we did here. But of course, in numbers, we usually use lowercase letters A, B, C, but in sets, we use capital letters. Okay, let us try to investigate the first question. I don't want you to see if it is true or false, but I want you to tell me how it looks like. So, can you tell me how should I write the first one to see if it is true or false? Union distributive over intersection. So how should I write it down? Yeah, you can pretend that it is true or false. We don't know. I just want to see how it looks like. Then I can test if it is true or false. Yes?
Is it A union?
Just wait. This one, A union.
Then brackets B intersection C.
Is equal to what?
Is equal to A union B intersection A B C.
Yes. If this is supposed to be true, it looks like this. I am taking, so you can compare it. You see, this operation is more or less similar to this operation here, if I want to give the rules, and this operation is that. So everyone understands that? I'm not saying that this is true or false. I'm just saying that if I want to see if it is true or false, I have to know how it looks like, and then I can ask the question if it is true or false. Okay, let us momentarily jump to the second question. So how should I do that? How it looks like?
A intersection.
A intersection.
B parenthesis B union C.
C.
Equals A intersection B union A intersection C.
Yes. So these are the cases. If this is going to be true, then this is always the case. And the good news is that in this case, both of them are true. But we will not be able to prove it rigorously. That is not part of your lesson. Okay? Both of them are true. The only thing we can do at this level is to investigate them with some examples. Of course, examples are not proof, I know that. But it is at least investigating that this might be true. And we can also use Venn diagram to visualize what is happening. But that is at most what you need to know. But you need to take my words for granted that in this case, both of them are true. But the other case, only one of them was true. Okay? Okay, let us try to understand this. First from some very simple examples. Okay, so I have these examples you see here on the board. I want to take the same A, the same B, and the same C and investigate one of them. Only for this example to understand how it goes, yes? So let me write my sets here. So the set A that I have given to you here from the beginning is 1, 2, 4. And the set B is what? 1, 5, 7, 4. And then I also gave you another set on top of that board, C, 2 and 9. Okay, for example, I don't know, let us pick one of them. We can check this one, okay? Let us check this one is correct or not. So I have to check what is the right hand side and what is the left hand side and see if they are equal. Okay, this is not a proof. This is just an investigation that it might be true. Okay, so what should I write? For the left hand side, I have the set A. This is my set A, 1, 2, and 4. After set A, I have the union operation, a pair of brackets. Inside the pair of brackets, I have the set B, which is 1, 5, 7, and 4. And then after B, I have intersection, and then I have C, which is 2 and 9. Okay, but if I ask you to continue forward, which operation has priority here? Why? Because it is within the pair of brackets. So you have to copy and paste the first part. It has to wait 1, 2, and 4. And then you do this intersection. So what is this intersection?
Yeah.
Oh, so that was not very good. Okay, the empty set. Oh, so I have to write the union. Anyway, this is the empty set. And then if I ask you to union them, what the answer will be? The set itself, yes? So the left-hand side is this, okay? Do you agree? This is the left-hand side. The right-hand side, I have a pair of brackets. A is my set 1, 2, and 4. And then between A and B, I have union. Then I put my B. Yes? But after that, I have intersection, and then I have another pair of brackets, and then I have A, which is this set, this time union with C, but C is 2 and 9. This is the right hand side. But which operations have priority here? The union here, because this is within the first pair of brackets, the union there, because that's the second pair of brackets. So here I union these two sets, which becomes 1, 2, 4. I don't need to think, but now when I want to add, I have to think. 1 is already here, 5 I add, 7 I add, and then close. Yes? And then I will also have to do this one first. I union them. So I just write 1, 2, and 4, and then I start appending these elements if I haven't done that already. So 2 is already there, so I have to append only 9. And then when the result of this is clear and the result of this is clear, then I intersect them. So if I intersect them, what will happen now? The elements that are in common, what are those? 1 is here and there, that's correct. 2 is here and there, so I have to add it. 4 is here and there. Is there any other element which is in both? No. 5 is here, not there. 7 is here, not there. 9 is here, not there. So I have to close it. And then you see that number 1 and number 2, if you compare them, what do you get? You get that the left-hand side is equal to the right-hand side. I know this is not a proof, but this is better than nothing. But you have to trust me on that. So that is the correct, that is true. So you can test the other one yourself. So that's a good exercise. I want you to do that one yourself later. But before continuing, let us also, because that's also one of the exercises in the book, we want to understand if this is true using the Venn diagram. Okay, so let us try to investigate. Okay, so if I want to check the first one again using the Venn diagram. If I want to check equalities, I need to have two copies of exactly the same shape, but it is of course very hard for me to draw it by hand. But let us imagine, okay, or pretend that these are identical copies of one another. So if I want, here I have three sets involved. The most general case to draw is to draw them in that way, okay? And I will try to do my best to copy exactly. This should be the identical copy. Of course, this is not going to work very well, but you understand what you can pretend that these are identical copies of one another. In one of them, I want to find the left side, and in the other one, I want to find the right side and then compare the results at the end. Okay, but that's, yeah, you need to do it. For example, here, let us concentrate here, A union B intersection C. Because of pair of brackets, the priority is with intersection. So I have to intersect B and C in this picture. So this is C, this is B. Intersection between B and C means all the parts that they overlap. I hope that you agree with me that this red part is B intersection C. Yes? And now, forget about B and C. Only concentrate on this red region. Now you want to take A, which is this circle, and union it with this red region. Okay? What does the union mean? The union means the elements that are in one of them, at least in one of them. So you consider all the red parts, but I also need to add something to it. Yes. So these parts of A, which is not considered yet, should be added to the red part. Yes. Do you agree? So the orange one and this a little bit of red one includes A, and this other red one includes from B intersection C. So all colored region in total, it becomes the left-hand side. Yes, and if I want to, it might be a good idea if I draw a border around that shape. Yes, so what this shape, whatever inside, is the left side. Okay, and now we have to do the similar thing, identical picture here. But I have to find A union B. That might be a little bit harder because you have to visualize. So where is A union B? A union B means this part. This is just A, but I also have to append what is inside B. Yes? So this red is A union B. Agree? Okay, now I have to find A union C as well. So where is A union C? So let me take the orange pen. A and C. So here, okay, so I have to also go within C. Yeah. So you see, it's a very good tool to visualize things. So the orange part, A is A union C. Am I right? Okay. But now I want to intersect these two. So I have to find the overlap between the red region and the orange region. I want to see where the overlap is. Okay. Do you agree the overlap is exactly the same? Yes? So let me, of course, make it a little bit more clear because I also have to consider these, yes? These are also in C. Okay, so I need those regions that are colored in two colors, yes? That are dyed in two colors, or how do you say it, okay? So I hope that you agree with me. This part is exactly the part that we are interested in. Yes? These are the only parts that you see two colors there. And this is exactly the same as before. So it is a better way of understanding that this is true. Yes? We can do similar things. These are the exercises in the book, so you can just do it exactly for the second. Any questions so far? Okay, but now let me. So from this direction to this direction, when we go, we say that I am distributing. But can you tell me what happens if I want to go from this to, because when I have equality, sometimes I need to go from left to right. Sometimes it is useful from going from right to left. Okay? If I go from left to right, the name is distribution. But if I go from right to left, what is that? You can immediately understand it if I write it like this. Yes, because this is the most familiar example to us. This is distribution. If I go from left to right, I can, of course, sometimes I can go backward. I go from right to left. In that case, what the name is? What? Factorization. So here, if I go from here, I am distributing. When I go backward, I am factoring A out. Okay? So you can also say the same thing here. So if I go from this direction to that direction, I am distributing a union within this pair of brackets. But if I have this one and I need that, you see, this is in common. Exactly like that, this is in common. So I pulled A dot out, B plus C was left. I can imagine that I pull A union out, but what is left, B intersection C is left, and the same for this one. So factorization is also the same thing. By the way, these rules are not very emphasized in your book, but they could be also very fun. So you can do algebra with sets. For example, let me ask you about this question. I give you two sets without even telling you what the sets are. And then I write A union, A intersection, A complement intersection with B. Okay? So I want to teach you a little bit of algebra when it comes to sets. Okay, so of course, if I give you the elements, that is not a hard thing. You just know what to do. But I am just talking, we want to simplify things. I want to write something in front of it, which is simpler than that one. Okay, but it is equal to this one, even without knowing the elements inside A or B. So, what can I do? So hopefully you realize that I can use distribution law. Yes, distributive law. Because I have three sets involved, A complement, and B. One of them is union, the other one is intersection. So which version of these two are useful here in this problem? The first one, because union is outside, intersection is inside. Yes, so I can distribute it. So what happens? I take A union and distribute it within. So it becomes A union, A complement, and then A union, B. Yes? And then what should I put in between? Intersection. You see, I'm just following this formula. I'm giving the role of A to A. I'm giving the role of B to A complement, and I'm giving the role of C to B. Okay? And I'm copying and pasting that formula. Yes? But can I go forward? Yes, because we know what this is. A union, A complement is the universal set. And then I have intersection, A union B. Can I go further? The universal set intersection with the union of two sets. Can I write something in front of it?
The union of the two sets.
What?
It's equal to the union of the two sets.
Yes, because we learned here, it's still on the board, yes? If I have any set, no matter what that set is, if I intersect it with the universal set, the answer becomes the set itself. Okay? So this is a set, I don't know what that is, but I am intersecting it with the universal set. According to that rule, it becomes A union B. Oh, yes, that's good. So you see, I was able to simplify this. So A union A intersection, A complement intersection B with B can be written simpler as A union B, even without knowing what A or B is, okay? So this is called algebra of sets. So you can simplify exactly like expressions in algebra that we open, expand, and simplify. We can also do the same things here. Okay? Any questions here? For example, let us see if I can give you one more example. What do you think will happen about this? I have A complement outside. Let me write it B complement. And then I want to intersect it with A union B. So what can I do now? So again, I hope that you understand this is also distribution. Yes, because I have three sets involved and I have two different operations. But this is not the first distribution law, this is the second one. Yes? So you can give the role of A to B complement, give the role of B to A, and give the role of C to B, and rewrite the formula. So what happens, of course, I don't want you to look at the formula because distribution is not hard, yes? You take this one intersection with the first one, yes? And then what you can do, you can take this one with that one. So, but what should I write in the middle? Union, yes? Okay, can I go forward? For this one, I cannot write anything unless someone tells me what A and B are. But for this one, I don't need someone to tell me, yes? So I copy and paste the first part. But what is this one? The empty set. It's intersection of any set with its own complement is the empty set. So it becomes the union empty set. Can I go a little bit forward? I have a set, I don't know what that is, but whatever it is, I am unioning with the empty set. What is left for me? The set itself. So when you union something with the empty set, you are doing nothing. So it becomes B complement intersection with A. So that set, whatever it is equal to this set. And this set is more compact, so it is better to write it. It's like simplification, but we learn to simplify algebraic expressions. Here we are simplifying sets. Yes? Okay, let me ask you another question. That's also an exercise in the book, but they are not giving names to this. What I'm just doing, I'm just giving you the names. Now, let me give you two sets, A and B. And what I do, I would write A union, A again, intersection B. Okay, so let us see, can I simplify it using algebra that we learned here a little bit more? So the first impression is to use distributive law. Yes, that is correct. Because I have three sets involved. Of course, one of them is repeated. But one of them is union, the other one is intersection. So if I want to use distribution, let us see what happens. So what happens? I have to write A union with A union with B. So A union with A union with B, and the middle one should be intersection. But can I go a little bit further here? Yes, because A union A, we'll learn what is that? Is A intersection A union B. Actually, it is not simplified that much. The only thing is that what I discovered is true, but I couldn't say that it's simpler than that one, yes? Because the only difference is that here I have intersection, here I do. So it is not wrong, but if I can simplify it, it would be better. Okay? Can you intuitively think what should be the answer of that one? Let us use a Venn diagram to understand what the answer is. This is not wrong, but this is not that simple that I expected, if it is possible to simplify it. So this is why Venn diagram is a very good tool. So if you take A here, if there is no relation between A and B, draw this picture. It is the most general case. Okay? And now if I ask you, I want to see what the result is. What is that? A intersection B is here. And now A is the whole circle. But I am interested in unioning them. So on the one hand, I have the whole circle. On the other hand, I have this orange region. And I want to append them, okay? But I'm not allowed to repeat something more than once. So what do you think will happen?
Get A.
Get A, do you agree? Because if I have my A, and then I want to append the orange part to it, so I'm doing nothing. So what I expect the answer should be A. Okay? But the answer, it's reasonable to think that this is A, but of course I couldn't prove it mathematically like that here. I got something which is true. You can check, by the way, this one as well. So if this one is A, and this one is equal to this one, then this one should also be A. Let us check if that is true as well. So I draw a Venn diagram. I have this A, and I have this B. Here I have A union B. A union B is this part. Okay, this is A union B. But I have to intersect the union, which is the orange part, with this circle. I want to find the overlap between the circle and the colored region. So what do you get again? A itself. So that is correct. This one is also A. Okay, even though it is clear from the diagrams, Venn diagrams, that this should be A, but apparently there is no point if I use the distribution here. I go back. So it becomes like a loop. Okay? But according to the Venn diagram, I can do much better. I can just simply write A. Instead of having this, I can just simply write A. Why do you think this is correct? This is interesting to prove. And it is exactly at the right level. For example, if I start from here, I just want you to see that what I am doing is legal. I want to simplify that. One immediate way was using distributivity, but it didn't go anywhere interesting. So we have to change our strategy. The strategy that I want to use, I want to copy and paste everything here. I took and copied and pasted them here. But instead of A, I would write A intersection the universal set. Okay, so you need to be patient to see why it works. But first of all, do you agree that I can do this? Because this part is just copied and pasted here. And if I say what is A intersection the universal set, the answer is A. So it is legal to replace A with this one because they are equal. But now can you see why this is beneficial? Think about factorization now. Can I factor something out here? What is in common here and there? A with which operation? Intersection. So I can pull this out. I told you that one way is distribution, the other way is called factorization. So what we do, I pull A intersection out. What is left from the first one? Universal set. And then what is left here? B. But what should be the operation between? U. Okay? But can I continue further here? Yes. Because the set union with the universal set, I copy and paste the first part, but I can write something for it. What is that? The universal set. But can I go forward again? Yes, because intersection of A with the universal set is the set itself. So that is a rigorous proof of that if we take the distribution for granted. Okay? So you see that Venn diagram is a very good tool in our hand because Venn diagram was able to predict what is the best answer. Okay, so this is very important rule. And these rules, I write them for you This has a name in set theory. They are called absorption laws. So absorption laws are like distribution laws, but one set is repeated. Okay, so for example, A union, A intersection B, or A intersection A union B. It is like distributive because one of them is intersection, one of them is union, but the difference is that one set is repeated. Absorption laws tells us that the answer is the repeated set. Okay. You don't need to know the names. These are within the exercises, but I want you to know that the exercises are designed based on the laws that they know. Is that clear? Okay, there is also another one which is a level 3 problem in the book, and I want to do that. And that's also a very important rule or law. And it carries the name of a mathematician, De Morgan, yes? So those are called De Morgan laws. I don't think the book has named them, but this is a level 3 problem in the book. I want to ask your opinion, okay? I give you two sets, and you union them, and then we want to find the complement of the union, okay? We want to see how this is related to the complement of the individual sets A and B. Yes? Is that clear? So, I give you two sets, you union them, and then take the complement. It becomes a set. Now my question is that if I take the complements first, for example, this is something that comes to mind. Okay? Is it true or false? We want to see. It should be false. If you see by Venn diagram, it is false. Yes? Can you see directly from the Venn diagram that this is false? Because when I say A union B, this is the orange part. When I want to complement the orange part, I have to be outside the orange part. So it means that everything within the rectangle, but outside the orange part. But when I say A complement, even if I don't care about B complement, A complement means outside A. When I say outside A will also include this part, which is not correct. So that is definitely not correct. So if I union the sets first and then complement, it is not the same as if I complement first and then union. Okay? But it turns out that this one is true. Okay? So if you want to complement a union, you can complement individually, but instead of taking union, you have to take the intersection. And there are two laws. One of them is for union complement, the other one is for intersection complement. If you intersect first and then complement, it becomes if you complement first, but instead of intersect, you union. So these are exercises in the book, and then they have asked you to prove them rigorously. Of course, we can also use Venn diagram to see why this is true. Yes, but let me see. We have a little bit of time, so let me take one of them, and then prove it in both ways. One using proof is only one way, and that's mathematical proof. Represent it here. Let us take, for example, the first one. the first one using Venn diagram. This is investigation, not proof. So I have to have, because I want to prove an identity, I have to have two identical pictures, and the most general case for two sets is considering this scenario. And this is my universal set, and then I will draw another one. I have to copy and paste exactly the same thing. A and B, the universals. Okay, so let us try to start coloring things. I want to have A union B complement. Okay, so let us not mess up. Where is A union B complement? It means outside the union of A and B. Okay, so it means that the union, do you agree? The border of the union is here. This is the border of the union. Means outside this border. So let me just color it with some, I don't know, green here. So this, what I am highlighting, okay, so this green part is A union B complement. Understandable? Okay, but now let us go here. I have to find A complement, B complement, but this time I have to intersect them. Okay, might be that's a good idea. I use different colors. So first concentrate on A complement. It means outside A. So outside A means here. Every place that is outside A should be covered. Yes, this is outside A. Okay, B complement, let me change my color. B complement means what is outside B. So let me do it horizontally this time. Whatever outside B should be covered. I hope that this is good enough. Yes, so outside B. Am I right? Outside B. So outside B is the orange color. Outside A is the red color. But now I am interested in the intersection. It means that I want to find all regions that are colored with two different colors. Yes? What is that? Do you agree that this is the case? Yes? First of all, you see that outside these two circles, we have two colors everywhere. So those are acceptable. But now if I go here, no colors at all. If I go here, one color. If I go here, one color. So the only place that you see two colors is exactly the same region that you see in this picture. So this is from Venn diagram point of view to convince yourself that this is indeed the case. But that is not a level 3 problem, of course. The level 3 problem is that you want to prove it. Okay, so I would prove it in that way. If I want to prove two sets are equal, I need to convince you that the elements are exactly the same. Whatever is in this set is also in this set, and whatever is in this set is also in that set. If I can convince you that this is the case, it means that whatever you see here, you see there, and whatever you see here, you see there. One of them is not enough. If I say whatever is in here is there, is it guaranteed that they are equal? No, because it might be here we have some extra elements. Okay, so we have to convince them of both sides. So this is the starting point. I would say let X be an element inside the left-hand side. Let X belongs to this. We prove that X belongs to the other side as well. If I can convince you this is the case, it means that whatever is inside the left-hand side is also in the right-hand side. But this is not finished. Then I have to convince you that whatever is inside the right-hand side also lives inside the left-hand side. But let us start from here. Okay, now I want to ask your opinion. If someone tells you that X lives here, okay, then you can be sure that X does not live where?
A or B.
A union B. Yes. Because you say that X belongs to the complement of a set, whatever that set is. It means definitely X is not in the set itself. So this means X does not belong to A union. Let me wait for you to see if you understand that. Do you understand that from here I can conclude this? That is the meaning of complement. What was complement? Complement means the elements that are not in the set. You are telling me that X is an element in the complement of this set. It means that this element is not inside the set itself. Yes? Yes? Okay, now if someone tells you that X is not in the union, what can you conclude about those sets and X? Imagine X is not in the union of two sets. What can I conclude?
X is not in any of the sets.
X is not in any one of them. Because if it is in at least one of them, it should be also in the union. When you say X is not in the union, it means what? It means X is not in A and X is not in B. It is important not to write or. Yes? X does not belong to the union. It means that X is in neither of them. Because if it is in at least one of them, it should be also in the union. Yes? Now that X is not in the union, it means that it is not in any one of those. Okay, but now if I tell you X does not live in A, what can you guarantee?
X lives in a complement.
A complement. Yes? X lives in a complement. It means X belongs to a complement. And if I guarantee you that X does not live in B, then it means that you can guarantee that X lives where? In B complement. Yes? And now look, I have an element which I know lives in AC. I also know the same X lives in BC. So X is an element both for AC and BC. So it means X is an element in overlap. So what does it mean? It means X lives where? Yes? X belongs to a intersection of them. X is an element which is in both of them. According to the definition of intersection, definitely X lives in the intersection of them. Okay. But of course, this proof is not finished because you just showed that whatever is on the left, in the left, is also in the right. But we should also do the other way around. So I'm a little bit lazy to do the other way around. So, but I want to check if it's possible or not. So this time, I start from here. I take an element inside the right side. I want to convince you that that X also lives in the left side. Okay, let us see that if these arrows are reversible. Yes? So I start from this one. Can I go backward and conclude this? Yes, because you are telling me X is intersection of two sets. So it means that X belongs to both of them. Otherwise, it will not be able to be in the intersection. X is in the intersection. It means X is in both of them. Means X belongs to the first one and X belongs to the second one. So this arrow is possible to go backward. Okay, now someone is telling me that X belongs to A complement and X belongs to B complement. Do you think that I can go backward and conclude that X does not belong to A and X does not belong to B? Yes, because when you say X belongs to A complement, it means that X does not belong to A. And the same story for that one. Now the question is that, do you think I can go backward here as well? If you tell me X is neither in A nor in B, can I conclude that X is not in the union?
Yes.
Yes. So that is also reversible. And then if X is not in the union, it is in its own complement. So you see that I can choose an element on the left and go show that that x belongs to the right, and I can also start from an element in the right and show that that element belongs to the left. So it means that these two sets have identical elements, so they have to be equal. Yes? Is that understandable? Okay, so for example, let us assume that the formulas are here. Can we simplify this a little bit? For example, I say that A intersection, then I would write B complement, and then I would write intersection A, and then I put a complement up there. Can I simplify this using a set algebra? I will not give, this question is in the book, but I will not give these type of questions, okay? But now that we are talking about them, it is good to know about them a little bit. So can I simplify this as much as I can? Yes?
Is the distribution rule?
No, I cannot use distribution rule right away. Yes, because first of all, they are the same. Secondly, the complement should be done first. So we also have some priority. So the priority is with the operation within the pair of brackets, and then complement, and then others. Okay? So here, I cannot start distribution immediately, because you see that first of all, they are the same. And then this is captive of this one. So this is held prisoner by this complement. You have to do that one first. Yes.
B complement intersects A complement, it becomes B union A complement.
Yes. Why? Because I can use De Morgan's law here. I copy and paste this one. Yes. And then this is intersection. And I want to complement an intersection. This is this second rule. If I have an intersection, I want to complement it. De Morgan tells us, take the complement of each one of them, but instead of intersecting, you're supposed to union them. So I will do the same thing. So I open a pair of brackets, I complement each one of them. Yes? But instead of writing intersection, I write union. That's the first step. But we learned something about B complement before. So what is that? It's just B. So I copy and paste this one, and then it becomes B, and then union A complement. Can I go further now?
Now you can use it.
I can use distribution law. Yes, so it becomes A intersection B, union A intersection A complement. But A union intersection A complement is what? Is the empty set. And every set union with the empty set becomes equal to itself. So even by Venn diagram, it is not that easy if you want to visualize it. I mean, you can just do it yourself. If you want to draw a picture to see that this is exactly A intersection B, you have to be careful about coloring them, keeping track of the regions that you are coloring them. But the algebra is not that hard, and it is always true. So is there any questions regarding here? So this expression, whatever it is exactly equal to A intersection B. You can test it yourself. You can take a Venn diagram, try to understand this calculation just by visualizing the Venn diagram. I don't think it is that easy to immediately come up with the correct answer. Okay? And even if you do, that would be one possibility. You have to consider all other possibilities. Any questions? No? Do you know when the lesson ends?